Hello and welcome to Section 5, Intervention Queries, Identifiability. This is what we covered in the previous sections, and we saw that Bayesian networks are capable of answering probabilistic queries. CBNs are capable of answering intervention queries, but in particular, we want to focus how can they do that in the presence of latent or unobserved variables. Here's the example. The COVID example, this time we're assuming that this network is causal, so it's capable of answering intervention queries. But this time we're assuming that social distancing, COVID, and season are unobserved. For COVID, for example, this means that these conditional probabilities, the CPDs of fever, condition on COVID, cough, condition on COVID, and difficulty breathing, condition on COVID, these are unknown. We cannot use the standard techniques from like MLE from parameter learning. They don't have missing values, they're completely unobserved. And the reason could be, for example, we're in the beginning of a pandemic when the effect of COVID on these variables are unknown. We don't know how COVID, for example, affects fever. Okay, now the question is follows. Can we answer the following query without performing the actual intervention? So does an individual take drug if the individual is somehow forced to cough, okay, like by taking a certain medication or exposed to certain environment or weather condition, will then the individual take the drug? So we can factorize this probability into several CPDs, but we should be able to do that without using these CPDs, and that's the whole point. Okay, we saw that given a causal Bayesian network, intervention queries are answered via mutilation. This was done, however, without performing an experiment. So, for example, if I was calculating P of y condition on do of x, we didn't literally go there and actually perform an experiment where we fix the value of x to 1. We did it without performing the experiment. The intervention query was treated as a probabilistic query in the mutilated network. It was answered by using the CPDs of the observed variables, which can be estimated using parameter learning. So if I put all of this together, I have this truncated product formula. Consider random variables y with probability distribution p, given a causal Bayesian network that is compatible with p, and a subset of variables z that I intervene over, P of y, so all of the variables, P of y conditioned on some of them being intervened, this is equal to the multiplication of the probability distributions, the CPDs, of y conditioned on its parents over all variables except for the intervened, because the intervenes are basically equal to 1. This is a perfect intervention. So I don't have any difficulties if I have all the variables observed. So again, such a simplification of the intervention query was possible because of the implicit assumption that all causes are included in the network, meaning that we see all of these P of y condition on their parents. So I could just use this and the definitions of probability, conditional probability, similar to chapter 1, I could perform the rest of the calculation for the intervention. But we can have unobserved variables, perhaps the most important of which are confounding variables. A little story here. Last week was Arya's 5th birthday. His parents gave him a small party and a birthday cake. Arya remembers that he had a birthday cake also at last year's party. And now he thinks that there should be a birthday cake at every party. So what's happening here is that the association between birthday cake and party is observational. That is something that Arya observes. But this does not always indicate a causal relationship. There's another variable that causes both birthday cake and party, and that is the birth date. Arya doesn't see this hidden cause, so the only way for him to associate the two variables is to link one to the other. To assume one of them, say party, is causing the birthday cake. Here, birth date is a confounding variable, a common hidden cause. So what's the impact? Here's an example, the Simpson's paradox. Imagine that the recovery rates of 700 patients are recorded. Half of them use the drug, half of them use the placebo, and here are the results. From this table, we can see that there is an association between drug and recovery. The probability of recovery of an individual, if the individual did use a drug, was less than if the individual did not use a drug. Okay, so it's kind of suggesting that it had like a negative effect. But here's the interesting part. The probability of recovery, given that the individual used the drug and was a male, was greater than when the individual did not use the drug. Okay, and the probability of recovery given that the individual was a female and used the drug also was greater when if it was given that the individual did not use the drug. So exactly the opposite of what we see here. I mean, this is quite interesting because the first one is saying that if you don't know anything about the gender, then then you know that the individual used the drug, then the individual is less likely to recover. But then once I tell you that the individual was a male or was a female, and it's one of these two, then it's exactly the opposite. So is there a paradox here? The answer is no, and the reason is that gender was a confounding variable. Women were more likely to take the drug than men. Gender also impacts the recovery, so gender is a common cause, and it was hidden to us. So it was a confounding variable. And we also know that drug impacts recovery. We can have this link. So the causal graph would look like something like this. Now you may say, how do you know that drug impacts recovery? Well, even if the impact is 0, I can still have this link, and then in the probability, in the CPDs, it will appear to be 0. We saw that already, that having an extra link is fine. Okay, so now using this DAG, if an individual is forced to take the drug, then it will be fixed to 1, the value of drug, and gender will have no effect on drug, so it will be a mutilated network like this. Now, if I want to truly conclude about the effect of drug, rather than answering observational queries, we should compare these two intervention queries, the probability of recovery given that we force drug to 1 or force drug to 0. And we can see that using this mutilated network, this will be equal to the summation of P of R condition on D and G times P of G over when we do the summation over G. Okay, it's just as simple as here. Now, by doing this, note that I'm assuming that I have access to the value of gender or to the corresponding CPDs. Okay, I'll get back to this soon. So from that and from the table, I can calculate the intervention query for when we force the drug to 1, it will be 0.83. And for when we force the drug to be 0, it will be 0.78. And therefore, ACE of drug on recovery will be the difference of these two, which will be 0.05, which is positive. So drug indeed had a positive impact on recovery. Now, okay, so we were able to kind of solve the Simpson's paradox by using the DAG here and noting that we had a confounding variable. But just note that the relationship that we wrote here, this is again when we have access to these CPDs. If I didn't have the gender in the table here, if it was truly unobserved, if these were not recorded, if we just had this last one, then we couldn't really answer the intervention query, because I then could not replace these CPDs, the values of these CPDs here. And that's the difficulty that a hidden variable can bring, a common cause or a hidden cause can bring. So I want to elaborate further on this via an example. Consider random variables x and y with a correlation between them. The goal is to determine p of y condition on do of x. We know that x is causing y. Imagine this is given, but we are unsure if the correlation is also due to a confounding variable h. So the causal network over the variables x and y is this, when we assume that there is no hidden cause. Now, if x is truly the only cause, p of y condition on do of x will be simply p of y condition on x. Okay? The mutilated network will be this. There's no special change. However, if there is a hidden common cause, like this, and this is a bow notation, which we will often use later on. Sometimes we may not even put the h here. This means that there is a common cause, a hidden common cause between x and y. Okay, so if there is a hidden common cause, then the answer depends on how much y is influenced by the common cause. Here. In the extreme case, where all the effect is coming from the common cause, nothing from x, then it will be, this intervention will be equal to p of y. Right? So it will not depend at all on x. It will completely depend on h. So if I intervene on x, it will be simply p of y. Okay? So using the same CBN, a causal Bayesian network, this is what I was using. Just with the here, it's still the CBN is xy. This is just a notation to indicate that there was an extra variable that we didn't model. So using the same CBN, we may get different answers to the same intervention query, right? Just because of that hidden variable. Of course, we will get a unique answer if we use the underlying SCM or if we observe all variables. But this is in general infeasible to get all the exact equations, underlying equations of SCM, or to assume that we know all of the causing variables. Okay, that is often infeasible in practice. So we are interested to know when an intervention query can be answered using CBN and without performing an actual intervention. This means that the query should be breakable into conditional probabilities that include only observed variables. And this brings us to the definition of the so-called identifiable intervention query. An intervention query is identifiable if it can be answered using conditional probabilities involving only observable variables. Here's an example. X is causing both z and y, and there's a hidden variable h that is causing both y and z. And the question is p of y conditioned on do of x identifiable or not? And the answer is yes, because it equals to p of y conditioned on x. We will soon see why. Some intervention queries can be simplified using independencies in the mutilated network. The process is performed by 3 rules of do calculus. These rules are called do calculus. And to get there, we need some notations. Consider the causal DAG G, and suppose x, y, z, and w are disjoint sets of nodes in G. Let G x bar be the graph obtained by removing all the incoming edges in X. Gx underline be the graph obtained by removing all the outgoing edges from X. And then the 3 rules of do calculus for every intervention distribution are the following. The first one is called insertion, deletion of observations. And here we go. Okay, so consider the DAG, the COVID DAG in the following. And we want to answer the intervention query P of B condition on, so B's here, condition on do of C, and once we are given M, the value of M. So the point is that the only active trail between M and B is this one here, the red one. It's via C. Now this will be removed, this active trail will become inactive once we construct the mutilated network, because then these edges will be removed and you can see that there's no trail between mask and difficulty breathing. So we can simplify this intervention query to P of B condition on do of C. I don't need M anymore. It will become deseparated. Okay? And here we go with our first rule. If we have in a GX bar, if once I remove the incoming edges of the intervened variables, if we see that Y becomes independent of some observed node Z, then I can remove Z from the intervention query. Okay, so that brings us to the first rule, as I explained. Now, the second one is action observation exchange. Back to our COVID graph. This time we want to answer the query of P of V condition on do of M. Okay, there is an active trail MCBV, but this one is a causal direction. Okay, so it's really indifferent to V whether M is observed or if it's if we do M, if we fix it to a certain value, because this is a causal graph. So it will make its impact via COVID, and from there to difficulty breathing, and from there to ventilation. So I can simply remove the do operator. Okay, it's similar to when I just have, say, mask and COVID only, and then I intervene on mask. Well, then it's the same as when I just observe mask. Okay, the mutilated network will have no change in this network. Now, how can I translate it to a condition? The condition here, it's not about mutilated network, it's about G of M underline. So I have to remove the outgoing edges from the intervened variable, here mask, and if then I see that the ventilation is independent or deseparated from mask, then that means that there's no causal relationship once I remove the outgoing links. Okay, so intervening on M or observing it will be the same. I'm not saying I will completely remove M. I'm just saying that the only possible impact of M to V is via its causal direction, because it was independent once I removed this edge. So I can remove the do operator. And there we go with our second rule, which just generalizes our observation. Okay. Before going to the third rule, we want to go through an example. So here, X is causing Z and Y, and there's a link between them. This is the example we just saw earlier. A common cause H. This is identifiable because it equals P of Y conditioned on X, right? Why? Because Y is independent of X in the graph G of X underline. Once I remove these edges, then the two will become independent, so I can remove the do operator. Note that I cannot make the same conclusion for this graph. It's, again, X is causing both Z and Y, but the common cause is this time between X and Y. And the reason is that if I construct G of X underline by removing the outgoing edges from X, still Y and X will have an active trail via H. So Y will not be deseparated from X. Okay, this was the second rule. The last rule, insertion, deletion of an action. To cover that, we consider this causal network again, and here's our intervention query. This time we have B do of O, cough, and we observe U. So the active trail from B to the intervention variable, difficulty breathing, goes to COVID, and from there to cough. This is the active trail, but it becomes inactive once the graph becomes mutilated. Okay, so I remove the incoming edges to cough. So difficulty breathing here becomes deseparated from the intervened variable, and therefore I can just remove the intervened variable. the whole do of O. This is quite similar to the first rule. There it was not about do of O, it was about the observed one, like U here. And we saw that, well, if in the mutilated network B becomes independent of U, then I can remove U. Here it's kind of the same. I'm just saying that if it becomes independent of do of O, I can remove do of O. The only difference is that here it's G of X bar Z bar, because I need to remove, or let's say it's better to remove both the incoming edges to X and the incoming edges to Z, because both of them are intervened. There Z was just observed, and I couldn't remove the incoming edges to U, to Z. Okay, so this gives me more flexibility, more power. Great, this is the last rule. So I have all these 3 rules of do calculus. Now, here's the theorem, the completeness of do calculus. A causal effect, P of Y condition on do of Z, is identifiable if and only if, by using a finite sequence of these 3 rules, it can be reduced to an expression involving only observed quantities. So, first of all, if I can use a sequence of these rules and break down my intervention query into an observational one, then the query was identifiable. And secondly, if it's going to be identifiable, I should be able to use these to break it down into an observation query. Okay, so it is complete. But it's not always that straightforward to use these rules. Here's the first example we saw in this section. P of R condition on do of cough. Okay, there is a direct edge from cough to drug, so it can only be deseparated in G of O underline. If I mutilate the network, so I will remove these incoming edges to cough, then drug will still remain dependent on cough. So I cannot do anything with the do operator. In order to get rid of it, I need to use the second rule of do calculus and focus on O underline. So I will remove this edge, and then still I will see that there are 2 active trails, the cough COVID fever drug and cough flu fever drug. If I want to use the second rule, I need to somehow make these trails inactive. How can I do that? Well, COVID is not observed, so the only way to do that is to observe fever. So I can just include fever and marginalize it into the probabilities. Like here, P of R condition on do of O, I include F here, and then because I added it here, I need to multiply it by also by this term. This is the part I said it's not that straightforward to get to this equation. Okay, now how can I simplify this? I want to ideally remove the do's. The first term is what I intended to do, just to make drug and cough independent. So I can now use the second rule. Just note that I removed the outgoing edges from cough, so Z here, Z underline, is the same as cough, so I can remove the do operation from Z. I can make it an observation. So the same here would be to remove do from O and just to observe O. Okay. What about the second term, F condition on do of O? For this one, I can use the third rule. I have cough, it's being intervened, and I have fever here. Now, if I consider the mutilated network where I remove these 2 edges, then fever and cough will become independent. So I can completely remove do of O. And I will just be left with P of F. Okay, great. All these ones, O, F, and R, they are observed, so it was identifiable. Okay, but this whole process, this can be put in a compact way, the so-called backdoor criterion, to formulate it and to use it in other situations as well. Given an ordered pair of variables x and y in a directed acyclic graph G, a set of variables z satisfies the backdoor criterion relative to x and y if the following two conditions are satisfied. First, so I want to use this to explain the situation. I have x, y, and I'm going to define the backdoor criterion, a set of nodes z that satisfy these two conditions. No node in Z is a descendant of X. You see here, both of them are parents of X. This simply means that Z doesn't block the causal path. So here you see the X to Y. There is a causal path in blue here, and Z are not blocking it. Second, they are blocking all, Z is blocking all the path between X and Y that include an incoming edge to X. So the other possibility for X to somehow impact the probability is via its incoming edges, okay, which are called the backdoor path. So here Z should block all those backdoor paths, and then what remains is only the causal path. And but I know that in the causal path, I can remove do. Its observation and intervention is the same. So using this, I can simplify the intervention query P of y condition on do of x as follows. It will be P of y condition on x. You see that I removed the do, and z. I also need to observe z to make it independent, to deseparate, to block all those backdoor paths, times P of z. It's also a parent of y, so I also need to include it, but z was is not a descendant of x, so it doesn't depend on x, so I don't need to put condition on x here. So it's basically what we had just right here. I'm putting it in a general form. And just note that parents of x always satisfy the backdoor criterion because they're not a descendant of x, and they also block the path between x and y, but only if they are observable. Okay, so that is something we can keep in mind. Now back to the example we just saw. Here cough had one causal path to drug, and it had two backdoor path via COVID, fever, and flu fever to drug. So fever satisfied the backdoor criterion for cough and drug, and therefore we could simplify the intervention query into what we obtained there. Okay. Now note that backdoor is indeed derived from do calculus. This is not something new that we provided. It is just handy to sometimes use it as a separate tool. Okay, rather than going through all those steps that I used for do calculus, we can just use the backdoor criterion. That's all. Okay, a couple of examples. We have a structure, and the question is P of y condition on do of x identifiable in the following causal structures? So here x is causing both z and y, and I have the intervention, the confounding variable h. In this situation, I can use the backdoor. Set of backdoor variables is empty. So if I don't need any z to block the backdoor path of x. There is no backdoor path, and therefore the empty set will just satisfy it. So I can simply write down P of y condition on do of x is equal to P of y condition on x. This is another way to see that second rule of do calculus. Now, what about this structure? Well, here set of backdoor variables is either z, right? So if I just use z, what happens is that it's not a descendant of y, but it's also blocking all the backdoor path. One is xzy, the other is xhzy. Both of them are blocked by just z. You can also consider H and Z together, right? They also block, but H is unobserved. So I will just go with Z, and therefore then this inquiry can be simplified into an observational inquiry. So it is identifiable as well. Couple of unidentifiable structures. The first one is what we have already seen. X is causing Y, and there is a confounding variable H. The only way to block this active trail, the backdoor path, is to observe H, choose H as the backdoor variable, and then we can simplify the query, but we cannot do this. H is unobserved. And we can see that none of the do calculus rules can help us here to simplify this query. So it is unidentifiable. Similarly, for this structure, X is causing Y without any hidden variable. It's also causing Y via Z, but there we have a confounding variable H. And because of that, the only way again to block this active trail, the backdoor, is to choose H itself, and then we could simplify it in this way, but we cannot do that. H is unobserved. So for example, these ones, we cannot calculate them. Okay, so again, it's unidentifiable. One other here, X is causing Z1 and Z1 causing Y, but Y also has another cause, Z2, and there are confounding variables here and there. Now in this case, I could choose H1 to completely block the backdoor. Can I do it without H1? So for example, if I choose Z2, then yes, X to H1 to Z2 to Y is blocked, but then we have a V structure here. X to H1 to Z2, now to H2, this will become active. And then from here, it will make its way to Y. So the backdoor is not blocked. So I could, again, simplify it in this way, but doesn't work. Now, note that the backdoor is just a sufficient condition for identifiability. If it's violated, we cannot conclude that it's unidentifiable. However, here one can show that even do calculus rules, they don't work. They cannot simplify the query, so we conclude that they're unidentifiable. Okay, great. One other example, we have the following causal network describing the causes of thinness, metabolism, or an illness here. And the illness is not causing the metabolism. So it's a specific type of illness. Suppose that illness is latent. We don't know how it impacts exercise and thinness. It could be a new type of illness. Now the question is it possible to advise exercise without knowing if an overweight individual is ill? Well, we cannot use the backdoor criterion because I is not observable. So this backdoor path cannot be blocked. But M is observable and can be added to the query. So I can write it down as the summation over M when I marginalize it. Okay. Now I want to simplify each of these terms. So first, the blue one. To simplify this, I can use rule 2 to make M, I can turn it into do of M. Okay, so I had from rule 2 that if G of E, if I mutilate over E and remove the outgoing edges from M, and then if T and M would become deseparated, then I could remove the do here, or I could add it if it wasn't there. So you may say, why do we want to make it more complicated and add another do? We often want to remove it. Well, here's why, because then I can look into a different graph, E bar and M bar. Okay, so now I'm also doing on M, so that means that I can remove this edge as well. And now thinness becomes completely independent of E, so I can remove it. Okay, so I will have a P of T of this one, the original one, condition on do of E and M. It will turn into P of T condition on do of M. This is also intuitively correct. If you think about it, we're looking at the effect P of T condition on do of E and M. Well, the only way that the effect of E goes to thinness, it's via M. So it's the same as setting M to the value that is caused here by E. Okay. Now, how to further simplify this? We can just use the backdoor criterion, and this time we can use E to block the backdoor path from M. Okay, so we will write it down in this way. So the first term is simplified. The second term is quite simple. P of M condition on do of E. We can use the rule 2 E underline, so I can remove this, and then I see that thinness, M will become independent of E, so I can just remove the do, and I will have P of M condition on E. So the whole query will be simplified in this way, and it turned into an observational query. So the answer is yes, we can advise, even though we don't know about that illness. Great. Again, to generalize what we just did, here's the definition of the front door criterion. Given an ordered pair of variables x, y, and DAG G, a set of variables z satisfies the front door criterion relative to x, y if the following three conditions are satisfied. First, every directed path from x to y is intercepted by z. Second, there is no backdoor path from x to any of the variables in z. And third, x blocks every backdoor path from z to y. Here. If all of these are satisfied, and if P of x and z has a non-zero value, then the intervention query can be answered in this form. All of these are observed or observable variables. Okay, again, this is not something in addition to the do calculus, but it can be handy in some examples, in some situations. To summarize, back to our roadmap, we now focus on the CBN. It can answer intervention queries, all of them. If we have latent variables, then we should use do calculus to see if it's identifiable or not. If it's identifiable, then we can answer it, otherwise not. Thanks for your attention.